Hello everyone, welcome to GATE lecture series. Myself S.A.ENGG, Assistant Professor, Department of Electrical and Electronics Engineering, S.A. Engineering College. Today I am going to take the GATE topic on types of DC machines. Basically, energy can be convert one form of energy into another form of energy. DC machine is an electromechanical device which convert one form of energy into another form of energy. DC machine classified into two main category. One is the DC generator, another one is the DC motor. Both are a electromechanical energy conversion devices. Well, DC generator which convert mechanical energy into electrical energy, and DC motor which convert electrical energy into mechanical energy. So we can use as the DC machine as a generator as well as motor. So the basic principle of generator is the electromagnetic induction. According to Faraday's law of electromagnetic induction, whenever the conductor cut the magnetic lines or flux, the generator. So DC generator having two winding, one winding is the field winding, another one is the armature winding. Whenever the supply is given to the field winding which produces the magnetic flux, this magnetic flux which cut the armature conductor and EMF is induced. So this induced EMF which is the alternating one. But we are using the DC machine. So we have to convert AC EMF into a DC EMF by using the commutator. Commutator is a device which converts AC EMF into a DC EMF. That commutator should be mounted on the shaft of the DC generator. So the direction of the induced EMF which can be measured by using the Fleming's right hand rule. So in this Fleming right hand rule we have the three fingers. The thumb finger which indicate the direction of force, and forefinger which indicate the magnetics of flux lines, and middle finger which is used to measure the voltage. And next one is the motor. So DC motor, the working principle of DC motor, whenever the current carrying conductor placed in the magnetic field, it experiences a mechanical force. So this force only for the single conductor. We have the Z number of conductor for the DC motor. So the overall force, that is overall the twisting force, is act as the torque. Once the torque will be developed, the motor, the rotating part of the device, armature winding should be rotating. This is the basic principle of DC motor. When the voltage applied, the current flowing through the armature and magnetic field from the current, it's interact with the stator, that is interaction of stator flux as well as rotor flux which produce the magnetic torque. So this can be the magnetic lines can be, force of the line can be used by using the Fleming left hand rule. Fleming left hand rule is used to determine the direction of force. Next one is the type of DC machines. So for the types of DC machines, the different category of types is common for both motor as well as generator. So based on the winding, we can classify it into two main category: self-excited motor as well as separately excited motor. So excitation is nothing but giving supply to the machines. That is giving supply to the field winding. Whether we can give the supply to the field winding either external supply or without any external devices. If the DC voltage is given to the field winding by using any other of the external device like a battery, that type of excitation is called separately excitation. Coming to the self-excitation which does not require any external devices. So the EMF which is generated by using the voltage produced, generator voltage itself enough to produce the excitation. Under self-excitation we have the different category. One is the series wound, another one is the shunt and compound wound. Under compound wound, based on the windings, we can again classify it into long shunt compound as well as short shunt compound. So basically DC machines having two winding, one is the field winding, another one is the armature winding. The field winding and armature winding placed according to that the types of motor should be classified. So I'm going to differentiate the generator as well as motor types. So separately excited DC generator as well as separately excited DC motor. What is the difference between two windings as well as what is the voltage equation as well as current equation. So in DC separately excited motor, the armature winding, and this is the armature winding and this is the field winding, both are connected in parallel. In parallel connection, the voltage remains constant, but in series connection, current remains constant. In field winding, we are giving the external supply to the field winding. Once the winding get excited, so this winding should cut the armature conductor and EMF should be produced. That voltage is connected to the load. So V is the terminal voltage, EA is the EMF, RA is the armature resistance, IA is the armature current, IF or ISH is the field current or shunt current. So in this separately excited motor, armature current should be equal to the load current because this is the load path. Both are connected in series. In series, IA as well as IL both are same. While coming to the voltage equation, EA is the EMF, that should be equal to the V plus IA RA. So how much amount of voltage generated on the armature side equal to total voltage across the load side plus IA RA is nothing but voltage across the armature. And power equation, power equal to VA or EA into IA equal to. So we have the EA term and just we are going to multiply it by IA. V plus IA RA into IA. We get V into IA plus IA into IA square into RA. So this IA should be equal to IL, both current are same. So what is the armature power? Armature power equal to output power plus armature copper loss. We know I square R is nothing but copper loss. V into IL is nothing but the voltage, output power. And coming to the DC motor, the main difference between generator as well as motor is the armature current. From armature to load, it represents the generator, and load that is applied to armature, we have the minus sign here. So separately excited motor, IA equal to IL, but EG equal to EA equal to V minus IA RA. So the same formula followed here. Instead of generator, we have the plus sign. In motor, we have the minus sign. Next one is the shunt wound DC generator and shunt wound DC motor. So what is meant by shunt? Shunt is nothing but parallel. The armature winding as well as field winding both are connected in parallel. So this type of shunt motor does not having any external supply. The voltage. So here we have the node here. So according to the Kirchhoff's current law, armature current IA equal to IL plus ISH. ISH is nothing but the field current or shunt current, where ISH is equal to V by RS. In both winding, voltage must be remains constant. Voltage must be remains constant. So in this shunt motor, the number of turns should be very high because we have the resistance, high resistance value. In field winding, having the high resistance value to minimize the current value. The total armature current divided into two parts. One is the current flowing through the shunt winding, another one is the current flowing through the load side. So for that, we have to maintain the high resistance here. Number of turns should be very high. So voltage VA equal to V plus I into RA. While coming to the DC wound motor, IA equal to IL minus ISH. ISH is equal to V by RSH. EA equal to V minus RA. Same equation only, we have only sign changes. For generator we put plus sign, in motor we put minus sign. Next kind of DC machine is DC series generator as well as DC series motor. In this DC series motor, armature winding and field winding both are connected in series current. In series connection, we have to maintain the high current value. For that, we are putting the turns. Number of turns should be very low. So in this, the current value should be same. IA equal to ISC equal to IL. Well, coming to the voltage equation, EA equal to V plus IARA plus IARSC, because we have the series connection, voltage must be different path. So IARA is nothing but voltage across the armature. IA into RSC is nothing but voltage across the series winding. So the total voltage is equal to V plus IA into RA plus RSC. IA is the common factor. While coming to the DC motor, both current are same. EA equal to V minus IA into RA plus RSC. Next type of motor is compound motor. Compound motor is nothing but combination of two windings. So the field winding should be connected in parallel with the armature. Some number of windings connected in parallel with the armature winding. Some number of windings should be connected in series. That's why we called as the compound motor. In short, again we classified into short shunt compound motor as well as long shunt compound motor. In short shunt compound motor, the field winding, a whole number of field winding connected parallel with the armature winding. Some number of field winding connected in series with the armature winding. So IA, the total current IA equal to ISC plus ISH. ISH is nothing but current flowing through the shunt winding. IA is nothing but current flowing through the series winding. So IA equal to ISH plus ISC, where ISC equal to IL and IA. Both are same. IA current, that should be equal to IL and ISC. Voltage equation, VA equal to EA equal to V plus I into RSC plus IA into RA. While coming to the short shunt compound motor, we having only the difference is minus sign. In this we have plus sign, and motor we have the minus sign. In long shunt compound motor, so partial amount of winding connected in parallel and partial amount of winding connected in series. In this case, IA current should be equal to ISC. So IA equal to ISC should be equal to IL plus ISH. And voltage equation, EA equal to V plus I into RSC plus IA into RA. That should be equal to V. IA, here IA and ISC both are common term, both are same only, so IA into RA plus RSC. So coming to the power equation, V into IA equal to IA equal to V into IA plus IA square RA plus IA square into RSC. Finally we get IA equal to V into IL plus ISH square RSH plus ISC square RSC plus IA square RA. The total armature power equal to output power plus shunt field copper loss plus series field copper loss plus armature copper loss. In this case we have only the minus sign. Next we are going to see the problem regarding the types of DC machine. First problem. A separately excited DC motor rated 400 volt, 15 amps, 1500 RPM drives a constant torque load at rated speed operating from 400 volt DC supply, drawing rated current. The armature resistance is 1.2 ohm. If the supply voltage drops by 10% with field current unaltered, then the resultant speed of the motor in RPM is, we have to round off the value. Given data, what is the supply voltage V? V equal to 400 volt, and what is the armature current here? IA equal to 50 amps, and the given rated speed N equal to 1500 RPM, as well as the resistance, armature resistance indicated by RA, that should be equal to 1.2 ohm. This is the given data. Now they are asking if the voltage is reduced by 10%. Already the given voltage is the 400 volt. If voltage is reduced to 10% means, that is 10% means 90% available voltage after that reduction. What is the new speed? The voltage reduced to 10% mean what is the new speed? So the given data is the rated value. What is the actual value? Now we are going to calculate the new voltage as well as new speed and back EMF value. And first we have to know the back EMF equation. So this is the motor. So motor back EMF equation EB equal to V minus IA into RA. For motor we have the minus sign, but in case of generator we have the plus sign. So first we have to calculate the back EMF value. And now what is the relation between back EMF as well as speed? Already we know in generator the EMF equation EB equal to pi Pn Z by 60A. Here Z is the number of conductors, P is the number of poles, and A is the number of parallel path. And Z, P, A both are constant. So we have EB proportional to pi into speed. And this is the separately excited motor. For separately excited motor, we have to maintain flux as a constant term. So EB directly proportional to speed. If the voltage, if the back EMF changes means automatically speed of the machines also changes. So first calculate the back EMF for given data. Given data we have to take the given data as the rated value. So back EMF for rated value equal to voltage minus IA into RA. What is the voltage value here? 400 volt, and IA is nothing but 15 amps. And what is the armature resistance value? 1.2. So 115 into 1.2 is nothing but 18. So 400 minus 18 is equal to 382 voltage. This is the given voltage. We have to calculate the rated value for given value. Given data is 382 voltage. Now coming to the problem, they are asking 10% of reduction of voltage. So we have to find the new voltage. So therefore new voltage is equal to, after 10% reduction means we have 90%. 90% is indicated by the 0.9 value. So given total voltage 400 into 0.9, we are getting 360 voltage. This is the new voltage after reduction. For this corresponding supply voltage, we back EMF new equal to V new minus IARA. IARA remains same value, just we have to change the voltage. So 360 minus 18. So 360 minus 18 is equal to 342 voltage. This is the new back EMF value. So already I told for separately excited meter we have to maintain the flux as a constant value because voltage is same. So back voltage is same for armature winding as well as field winding. So back EMF and speed. Back EMF is directly proportional to speed. So we have to take the two ratio. One is back EMF new value to rated value, that should be equal to speed new value divided by rated value. So we have to calculate the speed new value. Therefore N rated into EB new divided by EB rated is equal to 1500 RPM into 342 divided by 382. So we are getting 1343 RPM. For 10% reduction, the new speed value is equal to 1343 RPM. Without changing the unaltered means we have to maintain the flux as a constant value. If flux constant means automatically field current is also constant. So without changing any current value, we are getting the 1343 RPM speed value. Next problem, second problem. A 220 volt 15 kilowatt 100 rpm shunt motor with armature resistance of 0.25 ohm has a rated line current of 68 amps and rated field current of 2.2 amps. The change in the field flux required to obtain a speed of 1600 rpm while drawing a line current of 52.8 amps and field current of 1.8 amps. So last problem, we are maintaining the flux as the constant value, but in this case if flux changes, that is speed changes, means what about the flux value? So the relation between EMF and speed is EMF proportional to flux into speed. In separately excited motor, flux maintenance constant, but in this case we have the different scenario. The given data, N is nothing but speed, phi is nothing but flux, E is nothing but back EMF. VA equal to 220 volt, RA equal to 0.25 ohm. For given 1000 rpm, what is the given data? For 1000 rpm, that is represented by the N1 speed. For 1000 rpm, the line current is equal to 68 amps and field current equal to 2.2 amps. So this is the motor. So IA1 equal to line current minus field current. So 68 minus 2.2 equal to 65.8 amps. For this armature current, we are going to calculate the back EMF. For given 68.58, what is the back EMF value? So back EMF E equal to Vt minus IaRa. What is Vt value? 200 minus what is Ia? 65.8 into what is Ra? 0.25. So finally we get 203.55 voltage. For given 1000 rpm, we are getting the EMF value equal to 203.55 volt. Now second category, for different speed, that is for 1600 rpm. Now we are going to take that as a N2 value. N2 is equal to 1600 rpm. What is line current 2 value? 52.8 and field current 1.8. And what is the armature current? IL minus IF. We are getting 51 amps. For this 51 amps, what is the back EMF value? So E2 equal to Vt minus Ia2. And 220 minus 51 into 0.25 equal to 202.25 voltage. And we are going to take the ratio between two back EMF value. So E1 by E2 equal to N1 by N2 into pi1 by pi2. So we know the E1 value, we know the E2 value and N1, N2. But we don't know the pi1 as well as pi2 value. So I am going to maintain pi2 equal to, by solving this we are getting 0.6369 into pi1. So pi2 is equal to this value. Next we are going to use the flux reduction formula. Percentage of reduction in flux equal to pi1, that is given new first EMF value minus pi2 divided by the old value, that is old value minus new value divided by old value into 100. So we have to maintain pi1 as same value minus what is pi2? 0.6369 pi1 divided by pi1 into 100. So totally we have 36.3% of flux reduction value. And third problem. This problem is related to the generator problem. A belt-driven DC shunt generator running at 300 rpm delivers 100 kilowatt to a 200 volt DC grid. It continues to run a motor when the belt breaks, taking 10 kilowatt from the DC grid. The armature resistance is 0.02 ohm, field resistance 50 ohm and brush drop is equal to 2 volt. Ignoring armature reaction, the speed of the motor is dash rpm. So in this given problem, the machine which operated under two conditions. One is generator as well as motor. So we know DC machine which operated in both conditions. It can be operated as a generator as well as it can be operated as a motor. In this problem, we are going to see how the DC machine operated under generating condition as well as motoring condition. So the given data 100 kilowatts is the delivers power, so we can take as the output power. RA is P0 equal to 100 kilowatts and armature resistance is equal to 0.025 ohm and field resistance is equal to 50 amps, and this till 10 kilowatt from the DC grid. So from the DC grid means it indicates as the input power. So input power equal to 10 kilowatts. And specifically they are given the brush drop. So brush drop equal to 2 volt. So this is the DC bus. From the DC bus we have the armature winding and RF, and this is the shunt current, and this is the armature current, and this is the IL current. So first case, when the machine is act as the generator. So when the machine is act as the generator, IA equal to IL plus ISH. So the given data is P0 Vt. So from that we have to find the load current. We don't know the load current value. From based on the data, IL equal to P0 by V. We know V equal to power divided by voltage. So output power divided by voltage, 100 kilowatt divided by 200 equal to 500 amps. So next ISH current, I equal to V by R. So ISH is equal to V by RSH. So 200 divided by 50 equal to 4 amps. From the two data, we are going to calculate the armature current, IL equal to ISH. So we are getting 504 amps. So what is the generated voltage formula? EG equal to VT plus IARA. Normally brush voltage should be negligible voltage, but in this problem the brush voltage is given, so we have to consider that value also. So 200 plus 504 into 0.0252 equal to, so 214.6. so this voltage represent and the machine is act as the generator voltage. Next case, when the machine continue to run as the motor. So from machine continue to run as the motor, we need the input data. Input power equal to 100 kilowatts. From we have to calculate the supply current, and generator we have calculate the load current, and in motor we are going to calculate the load line current. So P in divided by Vt equal to 50 amps. So Ia equal to IL minus ISH. This IL is nothing but supply current. 50 minus 4, 46 volt. And what is the back EMF value? EB equal to V minus IARA minus brush. So finally we get 196.85. So machine can be operated both motor as well as generator, which can be decided by the based on the operation. Next, we know this formula, E proportional to pi into Ng. For generator I am taking G. So Eg proportional to pi G into Ng. So I want only speed. Speed Ng proportional to Eg divided by flux. For motor, Eb proportional to pi m into Nm. Therefore Nm proportional to Eb by pi m. So this is equation 1, equation 2. So from equation 1 and 2 we get motor speed divided by generated speed equal to back EMF divided by generated EMF into pi G divided by pi m. So pi is nothing but that is pi proportional to current. So pi proportional to current means that is indicated the field current. So pi proportional to IF. So for generator I am putting IFG, for motor I am putting M. So already I is nothing but V by R. So I equal to V by RF for generator. Same followed in motor, V by RF. So EB by EG into V by RF divided by V by RF. So V by RF, VA by RF getting cancelled, and remaining speed of motor divided by speed of generator equal to EB by EG. So I need only motor speed. So motor speed equal to Ng into EB by EG. So 300 into 196.85 divided by 214.6. Finally, we are getting 275.186. So the motor of the speed equal to 275.186 RPM. So the answer is 275.186. So thank you all.